Hello, welcome to Lecture 5. Today we're going to be talking about earthquakes. We're going to be going over what causes earthquakes, types of faults, types of earthquakes that happen. We're also going to be talking about effects of earthquakes, damage caused, other types of cool things that end up happening, as well as looking at how we can try to work on preventing damage, and why we feel earthquakes more widely on the East Coast but not the West Coast. So let's go ahead and get into it. Let's start with what an earthquake actually is. An earthquake is a sudden movement along a fault, meaning that you have a fault. We'll use our hands for this. You have a fault. They're sitting side by side like this. All of a sudden, movement occurs. And that's essentially what an earthquake is. A fault is going to be when you have two pieces of land, whether it's happens to be a border between continents. It's essentially when the land moves side to side very quickly. Most faults are locked up, and that is due to friction. And they suddenly will move when stress overcomes friction. The movement generates a wave of movement that we feel in the earth, and these are known as seismic waves. They will radiate from a hypocenter, which is where the slip occurred. This is under the ground. And at the surface, where we identify it, it is the epicenter. And this is what we're going to see here. You can see the bottom in the ground. We have the hypocenter right in here. And then up top, we have the epicenter. This is where we are going to triangulate where the movement occurred. So we're not going to say, oh, it happened over here on top of the fault, because you can see the fault goes at an angle. And we'll talk about why that is in a bit. Earthquakes can be caused by a variety of things. These include volcanoes, landslides, and impacts, but these are generally seen as weak causation, meaning the earthquakes they will create are not super strong or substantial. A volcano can cause an earthquake when you have magma moving underground, because remember, magma moves within dikes and sills, and as it does so, it actually breaks the ground apart, causes it to separate. When you have a landslide, that is a very large landslide, it will cause tremors to happen, just as if you have an impact. For example, a meteorite strikes the earth and you get a very large crater as a result, or a tsunami as a result. The impact itself is large enough to cause tremors to be felt widely. However, it's not as substantial or as destructive as earthquakes that happen due to fault movement. Movement along a fault is due to friction. Movement between plates or blocks doesn't really happen on its own, just like you can't just willingly slide across the ground as if you were on ice. However, since the plates are moving, you're going to have a buildup of stress, and when the stress becomes greater than the friction keeping the movement from occurring, it slips. And then elastic rebound, which is essentially how when you have a rubber band, you pull it and you let it go and it comes back together very quickly. That is elastic rebound. It will cause the then deformed rock that has slipped to come back to where it was in the undeformed position. And this is where you get your initial earthquake, and then you actually end up with smaller aftershocks because the ground is going back and forth as it goes back to its undeformed state. Plate boundaries and earthquakes are very important together. When you have convergent boundaries, where we have subduction happening, you're going to have compressional force, where things are coming together, just like how they form mountains. If you have a continental versus continental, continental versus oceanic, or oceanic versus oceanic also compresses plates together. And when subduction occurs, it is known as a megathrust fault. Subduction does not happen easily. It's not like you have something sliding around on butter in your frying pan. It's going to get stuck, just like if you didn't use butter in your frying pan. And so it will actually end up building up, and then suddenly shift as a piece goes underneath the other. This will form quite powerful earthquakes, the type that we see felt in Japan, Western South America, and the west coast of the United States. And this is exactly the type of fault that will cause a tsunami. Mountain building is also a thrust motion, but this causes specific faults, like a normal or reverse fault, to occur, which is due to the buckling and breaking of the crust itself. These also will create rather large earthquakes. So we can see here we have the subducting plate right over here. And again, it's not just going to easily go under, but it will form a megathrust fault as stress builds up due to slab pull and ridge push of the convergent boundary until it moves quickly, moves quickly, moves quickly. This is why we have such large earthquakes happening along the west coast of the United States, such as in Alaska, Oregon, Washington, and California. It's also why you have constant large earthquakes in Japan, Australia, and New Zealand, as well as Indonesia. All those areas that are around the Ring of Fire. And it is because of this megathrust fault which causes buildup movement, which causes the displacement of water and thus a tsunami. Again, convergent boundaries are compressional force, but what about transform boundaries? Remember, they don't create or destroy crust, but they do move side to side. These are what lead to transverse faults. Not all transverse faults are transform boundaries. Okay, they do cause the ground to become offset, but they are usually slow creeping. They'll have minor earthquakes, but they can be locked up under a large amount of stress for years and years and years, finally moving, causing more massive earthquakes, which is actually one of the fears related to the San Andreas Fault. And where you have maybe buildup happening over here, but there's movement over here, but over here there's not movement, and eventually it will move and you'll have these large cyclical earthquakes. Transform boundary or transverse faults occur in repetitive cycles, and though we can't exactly predict them, scientists can say another earthquake will occur and can measure the strain or stress rate and try to determine earthquake size before it happens. So here's an example that we see here of, thanks to a transform boundary in San Francisco in 1906, we have the offset of a fence and actually land being moved around. Seismology is the study of earthquakes, and geologists who study these earthquakes are called seismologists. They use machines called seismometers to measure the seismic waves. A seismograph is a different word for it, but most people use seismometer. And these are set up all over the world. They're used to track seismic activity. So if an earthquake is felt at multiple facilities, you can then triangulate the location of the epicenter. These work through inertia, which keeps the arm of the machine from moving while the ground moves the instrument, which amplifies ground movement. And these generate measurements known as seismograms. Today, they also have different types of seismometers, which involves a piece of technology that sits in the ground, just like it does here. And then it actually sends through, I believe through satellite information or GPS information, it sends the feelings that it gets to a facility where the arm moves back and forth, showing what that seismogram is feeling. We have these, for example, all over Yellowstone. We have them near major volcanoes because it is a way for us to tell when magma is moving. We also have them in areas where you have large fault lines. And so if you ever happen to see one of these containers where you see a block, please don't touch it. These are very, very expensive. There is a problem with people stealing them because some of the parts are very, they're worth a lot of money. So very lucrative. But please do not. They do use people do use grant money to buy them and put them in place, and they do cost a lot of money. So you're only hurting yourself if you take one. So from these earthquakes I mentioned earlier, we have seismic waves that are generated. Two main types of seismic wave that we're going to talk about here are body waves and surface waves. Body waves can be broken down into two types. You have the P wave and the S wave. P waves are also known as primary waves, and they can travel through solids and liquids. S waves, or secondary waves, cannot travel through liquid, thus they show up second. Surface waves, also known as L waves, only travel through the upper layers of the Earth, and they can only travel through solids. These are the ones that are going to make those big, wave-like ground motions that people who have lived in California have mentioned before. Also Oregon and Washington. If you've ever met someone who talks about how the ground came up to meet them, that's what was going on. So we can see here that your P wave is always going to arrive first, then your S wave and your surface wave. Sometimes they are very easy to tell apart, just like in here. Other times, not so much. They might be more on top of each other, or maybe you just have a P wave and no S wave. Sometimes they're small. So remember, the farther you get from the hypocenter, the smaller your waves will appear because they will lessen as they move through solids. Also, when P waves pass through a liquid, they will refract, just like when a pencil will when you stick it in a cup of water. And so that's part of a way you can tell us what kind of refraction was happening, and you can tell how far you are from the hypocenter. Body waves are, or P waves and S waves. We're going to talk about those for real quick. Primary waves are push and pull. So think of a slinky, where you're going to have compression and pull apart, whereas your S waves are going to have up and down motions, like when you shake a rope. So when P waves push and pull rocks in directions of travel, they can change the volume of material. They pass through solid, liquid, and gas phases, and they essentially make things go up and down. And you can feel P waves on the other side of the world, even if you physically can't feel it, your seismometer will. S waves cause the ground to liquefy, essentially allowing things to sink into it, and then it can be solid again, and this process is called liquefaction. These are your traditional side-to-side shaky waves that you think of. And they, again, do not travel through anything but solids. So some surface waves travel like ocean waves, where they make the circular motion, and others move side to side. It's actually the side to side that is worse, because that's going to cause the most infrastructure damage. So how do we tell the difference on a seismograph? Waves do show up at different times. P waves and S waves, since they travel through the Earth, will always come up first. P first, then S, then your surface waves will come. Your surface wave will lessen the fastest. It's also the last to arrive because it always only travels on the surface. Your reason S waves the reason S waves will come in second place is because of their 90-degree motion, whereas your P waves being compressional allows them to move quickly through the ground. And so we can actually see pretty clearly just where you have that first initial spike, where you're going to have the P, S, and surface waves. So now let's take a look at plate boundaries. This is the Circum-Pacific Belt and the Alpine-Himalayan Belt. We're going to split these up into two separate pictures, and we're going to talk about them separately. Starting with the Circum-Pacific Belt, also known as the Ring of Fire when we talk about volcanoes. The Circum-Pacific Belt is made up of subduction zones, or convergent boundaries, and will have 95% of all earthquakes in a year. Along these, you'll have megathrust faults, which will create the largest earthquakes, like what cause tsunamis. The Alpine-Himalayan Belt is earthquakes that happen along the Alpine-Himalayan mountain ranges. And these are due to continental collision, like India moving into Asia and Saudi Arabia and Africa starting to push up into Europe. Transform boundaries and ridges are where you're going to have weak earthquakes, like the Mid-Atlantic Ridge, the East Pacific Rise, the San Andreas Fault. Transform boundaries will have transverse and strike-slip faults, like the San Andreas, which will generate large cyclical earthquakes, but nothing along the lines of how large a megathrust fault can be. That's generally where your largest earthquakes are going to be found. Your mid-ocean ridge earthquakes that occur are weak because they are just due to tension pulling plates apart as magma comes up and it spreads the ocean. So here are some historic earthquakes east of the Rocky Mountains between 1755 and 2011. As you can tell, there's not a lot. On the East Coast and the central US, we don't have many earthquakes. However, the ones that do occur are really bad. And it's not just because we get larger magnitudes when they do happen. It's because they're felt farther, and it's because of the bedrock on the eastern coast being older. This is not new thanks to subduction or recent volcanism like on the west coast. It allows for waves to travel greater distances with less attenuation, meaning the earthquake will stay stronger farther. These are called intraplate earthquakes because they occur away from a plate boundary. An example of one more recent occurrence was in Washington, D.C., maybe about 6 years ago now, or 7. I have to double check. The earthquake caused a crack in the Washington Monument, and it was felt all the way up into Michigan and New Jersey. And here's an example of the kind of damage that we get on the East Coast. Again, just because of this older bedrock, the shaking is more intense, and you will have farther reaching damage. So the greater the interval between a P wave and an S wave on your seismograph, the larger the gap, as in like the larger the gap between the two of them starting, the greater the distance to the epicenter. So I'm not looking at end to beginning, I'm looking at beginning to beginning. So the first P wave, the first spike, and the first S wave spike, that is your gap. That's what you're going to count, even if it means counting part of that P wave. So you can use this gap to determine your distance. The larger the gap, the further you are. The closer the gap, the closer you are. And this can be used to help triangulate the location, because from that you'll end up drawing a huge circle around the location of your seismograph. And where it overlaps with another 2 circles, you will end up with your triangulated place, knowing here's where the epicenter was. So the question here is maybe, why only 2? Why not 2 seismograms? Why not 1 seismogram? Why does it have to be 3? So if you think about it this way, if we only had 2 circles here, we could have 2 spots where we would have the possibility of the epicenter occurring. And if we just use the blue and the orange, you would have a large expanse of area where this epicenter could also be. So by using all 3, you end up with 1 area where the epicenter may have been. Now let's talk about intensity and magnitude. Intensity is the measurement in the amount of ground shaking based on property damage, and magnitude is the quantitative measure of energy released in an earthquake. Magnitude is actually a more recent form of measurement. So let's talk about intensity scales. The first intensity scale we're talking about is the modified Mercalli intensity scale. It was developed in 1902, and we still use it today to describe the intensity of an earthquake. There is an online intensity map website, which was created by the USGS and is generated by user input, and that's where this modified Mercalli intensity scale comes in handy, because you get to generate maps like this, where it's, okay, who felt that earthquake? And people essentially click, and they talk about how highly they felt shaking, what kind of damage was done. And so one very cool and interesting thing you'll notice here is that a 6.0 earthquake on the west coast is only felt so widely, but a 5.8 earthquake on August 23rd, 2011 in central Virginia was felt throughout a very large portion of the eastern United States. Michigan, all the way up into Maine, New York, some people even in Florida felt it, which is pretty insane. And so this is how the modified Mercalli intensity scale works. You go from 1 to 12, 1 being nothing felt, maybe something around 7 means that, everybody's going to run outside because damage is negligible, but due to buildings being good design, but you did have a lot of shaking, to all the way to 12, which is damage total, waves seen on the ground, it's Armageddon, everybody's dead, okay? The next one is the Richter scale, and it is related to amplitude of the largest seismic wave, and this one is a logarithmic scale. It's an increase of 1 means 10-fold increase for wave amplitude. An inch increase means that there is 32 times more energy released from an earthquake. So for example, a 2 will have 32 times more energy released than a 1. And it is not very adequate for large earthquakes. However, it is the one that we do hear the most in the news. And this is how it looks. Our other magnitude scale is our moment magnitude. This will measure the total energy released based on the amount of slide, area of rupture, and strength of the faulted rock. This is much, much better for larger earthquakes. It's much more accurate. And it looks like this. And it goes anywhere from 1 to 9. A little, even to like 9.5, And it tells you an average per year of how many of these kinds of earthquakes you're going to get, examples, and types of energy released in equivalent kilograms of explosive, essentially TNT. So let's talk a little bit about destruction, the kind of damage that an earthquake causes. Magnitude and other factors determine the degree of destruction an earthquake causes. You will experience equal shaking around the epicenter of an earthquake in a 20 to 50 mile radius. This means it doesn't matter how far north, south, east, west, northeast, whatever, as long as you're in that 20 to 50 kilometer radius, you will feel it as if it was right there, essentially. Equal shaking. So you could be right on top of it. You could be 5 miles away, 5 kilometers away. You could be 10 kilometers away. You'll feel equal shaking as if you were right where the epicenter was. Earthquake damage is going to depend on a whole bunch of things. But once you're outside of that 50-kilometer radius or 31 miles, ground motion rapidly diminishes. Earthquakes in stable areas are felt less over a larger area. And structural engineers who build in these areas have worked to create buildings that can withstand shaking. Flexible wood and steel reinforced buildings withstand vibrations better, which is why buildings from ancient China are still standing and have stood through very large earthquakes, 8, 9. I suggest looking it up. Someone actually built a miniature scale of the Forbidden City to show how well ancient Chinese architecture withstands, to this day, high magnitude earthquakes. Blocks and bricks generally sustain the most damage because they are the least flexible material, whereas aluminum or steel will move with an earthquake better. Earthquake damage depends on intensity, duration, nature of surface materials, nature of building materials, construction practices, and you can see what kind of damage it'll do. So basically that means, are you on stable or unstable, consolidated or unconsolidated soil? Are you using material that's flexible? Are you working on building a building using blueprints that are intended to help preserve the building during an earthquake? Seismic vibrations are very cool. So remember, we talked about seismic waves, P waves, S waves. Well, they're going to cause things to move, vibrate, right? That's how you're going to move things through the earth. And if, let's say, you're in a unconsolidated or loosely packed, waterlogged area, you will have them start to behave like a fluid. And this is where liquefaction occurs. Liquefaction. This is how liquefaction can occur. When stable soil becomes mobile and rises to the surface like a liquid, it will cause these little cool looking like mud geysers. You can also have landslides, ground subsidence, and fires occur. And fires occur when, let's say, you have a gas pipe that ruptures due to movement, and all you need is a spark, and there is a fire. You also have electrical lines coming down. Those can easily catch certain materials on fire as well. But these vibrations lead the ground to become more like a liquid under stress. And this can cause a lot of very interesting things to happen. You can get sand volcanoes, and you can essentially get cars being pulled down, and then guess what? Everything passes, it solidifies up again. Now you have to dig your car out of the soil. These buildings rested on unconsolidated sediment, which acted like quicksand in the 1964 Niigata, Japan earthquake. I'll post a video as well in your Canvas page, so this way you can go watch it, which shows how quickly this happens and what kind of damage you get from it as well. Tsunamis, like I mentioned earlier, occur specifically with megathrust faults. Essentially what a megathrust ends up causing, or an underwater earthquake ends up causing, is displacement. A slab of the seafloor will get displaced up and then drops back, or goes down and then pushes back up. And so what that does is generates a displacement of water, creating a tsunami. In the open ocean, it will essentially just be a bump that can travel at very high speeds, not noticeable. But once we reach shallow water, where the size or amplitude of the wave can reach tens of meters in depth, it will cause a rapid withdrawal of water going pretty far back. And it almost looks like you can walk out into the ocean. It looks really cool. You can go and collect fish, shells, coral, etc. But beware! This will shortly be followed by what seems to be described as a wall of water. And this is turbulent. It can carry cars, it can carry trees, it will cause buildings to collapse, and it will pull things away with it when it recedes. A tsunami will generally strike 2 or 3 times, causing massive amounts of damage. So when a wave crashes, it is due to the fact that essentially the bottom part of the wave movement hits the floor of the ocean. With regular waves, this happens fairly close to shore, but with a tsunami, this happens quite far out, thus creating the massive wall of water that comes in. After the Hawaiian tsunami in 1946, we created the tsunami warning system. And this uses seismic observatories to report large earthquakes, deep sea buoys detect energy released from earthquakes, and tidal gauges measure the rise and fall of sea level. And you're probably wondering, well, what about that tsunami that hit Indonesia in 2008? Well, that is a different story. Everything has error. If something is happening and it hits a place too quickly, it doesn't matter that we have things set up to warn if the warning comes as the tsunami hits or too late for the tsunami to hit. So please be aware that when a large earthquake like this happens, if you're in an area that's very close, for example, a large earthquake and being in Indonesia, you have a potential to be hit by a tsunami. So as we know, I hope we know, the Earth has something called layers, meaning you have a surface, you have a mantle, you have a core. And within that, we break it up even further. Seismic waves help us see the inside of the Earth, and this is affected by the densities of the layer. Remember, seismic waves travel through liquid, some only travel through solid, and so solids aren't all the same density. We all know this based on maybe our own utensils and plates that we have. Some are lighter, some are heavier. Some material is denser than others, and that includes our own Earth. Some layers of the Earth are denser. And so what will happen is it will show that as seismic waves move through the Earth, which is pretty cool. Waves are reflected at boundaries and are refracted through layers and diffracted around stuff. So the velocity of the wave increases with depth if the stiffness and compressibility of the rock changes, and then can decrease if it becomes looser. And this can be used to interpret the composition and temperature of the rock. It can also be used to make some really cool pictures of what we see under the Earth. And so our Earth was created a long time ago when material came together, gases, solids, and accumulated and heated and spun. Spin, right? Iron and nickel melted. Being more dense, it settled to the core, and less dense material like oxygen, silicon, aluminum, along with calcium, sodium, potassium, iron, magnesium, and a whole bunch of other things, rose to the top, becoming our crust. This is known as chemical segregation, and it led to us having an iron-rich core and a primitive crust and mantle with 3 distinct layers: crust, mantle, core, which can be divided up into things like lithosphere, stenosphere, moho, lots of different terms depending on which area of science you are in, inner core, outer core. Let's talk about the crust. The ocean crust is about 7 kilometers thick. It is predominantly basalt, and it has a density of about 3 grams per centimeters cubed. Continental crust is about 35 to 40 and even up to 70 kilometers thick in some areas. Many types of rock make up the crust, but these are usually felsic. The density is going to be about 2.7 grams per centimeters cubed. The mantle has a solid layer extending to about 2,900 kilometers, and it is 82% of the Earth's volume. Chemical change at the boundary of the crust and mantle occurs, and your upper mantle, which is about 660 kilometers, is called peridotite. The upper mantle and the crust combined is known as the lithosphere. The weaker portion is below this, and it is known as the asthenosphere. The upper asthenosphere is partially melted, and the lithosphere does move independently of it. It kind of floats on top and moves around. creating really cool things like this. And then beneath that, we have the outer core and then the inner core. So now to deformation, a lot more interesting things happen here. Deformation encompasses all changes in shape, position, or orientation of mass, such as bending, breaking, when stress upon a rock is greater than the stress of the rock, or strength of the rock. And you have three types of deformation: elastic, brittle, and ductile. Remember that the strength of a rock is definitely influenced by its temperature, confining pressure, the type of rock, and when it has this stress put upon it. Elastic deformation is what happens when stress is gradual. The rock will return to its original shape after, and ductile or brittle deformation occurs when the elastic limit is passed. So remember, elastic is more like a rubber band. Brittle deformation results in fractures. It's common near the surface of the Earth. And ductile deformation is the solid state flow at great depths. This produces a change in the size and shape of the rock, and chemical bonds will break, forming new ones. Folds occur on a rock during ductile deformation. These are wave-like undulations that form when rock bends under compression. These compressional forces shorten and thicken the crust, forming anticlines and synclines. So if you want to remember it this way, anticline makes this shape, syncline makes this shape. Anticlines are upfolded or arched layers. They form an upside-down V or the top of an A, whereas synclines are downfolds or troughs, and they form a V. When they are together, they form waves in the land and are usually really easy to see, particularly with sedimentary rocks, because you can actually see the layers forming these folds. So the next time you guys drive up through Georgia, through the Blue Ridge Mountains, make sure to look out the side. You'll see these anticlines and synclines all through the road cutout. An overturned fold is when it looks like it's been folded in half. So you're going to be, instead of having it equal like this, it goes like this. And then your recumbent fold is when we're completely horizontal, recumbent coming from the word for sleeping or lying down. Domes and basins are another type of ductile deformation that happens when basement rock is pushed up and deforms overlaying layers of rock or strata, and it is circular or oval in shape and structure. It is called a dome, particularly when there isn't any broken parts or sheeting, which is a type of erosion. When the same type of shape forms, but it is sinking into the ground, it is called downwarping and forms a basin. This occurs when that material that may have pushed it up originally is removed, such as the removal of a magma body. Monoclines are large step-like folds that occur when large blocks of basement rock are displaced or thrust upwards. Ductile sedimentary rocks or strata will drape over the fault, forming more of a blocky slope than a break. Now we're going to talk about faults. Remember, faults are what happens when you have an earthquake. You're going to have movement along a fault line. Fault lines are fractures in the crust that result in displacement. These are formed by brittle deformation, and they have movement parallel to the dip and are called dip-slip faults. The rock surface above the fault is called the hanging wall, so it's where you would hang your lamp if you were thinking about being in a cave. And the footwall is the block that is below, where you would always walk upon. A normal fault is when the hanging wall moves down relative to the footwall and is accommodated by crustal extension. We can see that here. So when we have your crust moving apart like this, you'll end up having your hanging wall drop down. So let's go and look at this. So we see it right here. We have extension. Your hanging wall is going to drop, and you're going to have a resulting fault scarp, which is the low cliff that you see up at the top there that forms thanks to the hanging wall moving down relative to the footwall, and that little piece that hangs out over the top is a scarp. Here's an example of what a normal fault looks like in real life. And so now let's go ahead and go back to look at reverse faults. All right, so a normal fault and a fault block mountain is also due to extension. Essentially what you're happening is a whole bunch of hanging walls dropping over and over again, creating something called a Horst and Graben. So essentially what happens here is your uplifted block from the normal fault are elevated topography called horsts, and your dropped hanging wall is the basin, known as a graben. And so you'll get these really cool formations out, for example, in the Basin and Range area, like in Nevada, where you have a whole bunch of extension happening at once. Reverse faults and thrust faults are the opposite. These are due to compression, two spots moving together. And these will have a dip less than 45 degrees. So instead of, here's a whole 60, 45 degrees. And they result from compressional stress or crustal shortening. So essentially when you have two pieces pushing together like this. And so your reverse fault looks like this. You'll have your hanging wall move up instead. So it does this kind of motion instead of dropping down. And here is an example of what this looks like in real life as well. A strike slip fault is a type of transverse fault. It is also horizontal displacement and occur parallel to a strike, and they are side-to-side movements. Strike slip faults will occur in areas such as transform boundaries. So remember, large cyclical motion. Joints are not faults. These are just fractures. They actually have nothing to do with displacement, and they are a response to regional upwarping or downwarping, such as making a dome or a basin, and these are also known as jointing. Now let's talk about mountain building, because remember we were talking about crustal extension and crustal compression. Crustal compression is often due to mountain building. In the past, we've talked about Wilsonian cycles and orogenesis. Orogenesis is another type of cycle, which is the process of building a mountain. These are the mountain belts that we see today, the Appalachians, the Himalayas, and the Rockies. Older mountain chains have become eroded, like the Appalachian Mountains, and so are less topographically prominent, such as the newer ones, like the Rockies, which we see in here. Compressional mountains are when pre-existing sedimentary or crystalline rock formations have been faulted and folded, and you can see the stratolines in the mountains themselves, which is really, really cool. But with subduction, you'll get volcanoes and volcanic-related mountains. Subduction is a driving force behind mountain building for these reasons. Volcanic island arcs are island mountains. In continental volcanic arcs, you have mountain chains like the Cascades, and of course, accretionary wedges accumulate, forming mountain ranges, even if they're low, as well. This will form topography along continental margins. Island arc type mountain building is when you have mountains forming through volcanic activity, such as the emplacement of plutons that are uplifted and the accumulation of sediment from the subducting plate, which is what we get, such as accretionary wedges. And then we have Andean-type mountain building, which is due to continental arcs and Andean-type conversion zones, oceanic versus continental. Sediment will accumulate on a passive continental margin before subducting, which is what will create that accretionary wedge mountain, which generally will be sedimentary and metamorphic rocks being scraped off of the subducting plate. And it kind of looks like this. And so what you'll actually form here is something called a four-arc mountain range. Collisional mountain belts are made of some sort of collision, such as the Cordilleran type. This occurs in Pacific-like ocean bases where you have rapid seafloor spreading in places like the Atlantic, being balanced by rapid subduction. Island arcs and crustal fragments called terranes will collide with a continental margin. Some of these terranes may have been microcontinents at one point. These are subducted and larger ones are thrust into our continent, such as the North American Cordillera, which goes from upper United States into Canada and Alaska. These were due to microcontinents being shoved into the North American plate. Collisional mountain belts, such as alpine-type mountains, are the result from continental collisions, like the Himalayas. In this case, you're going to have a continent like India being shoved into the Eurasian plate, forming compressional mountain ranges like the Himalayas. The same thing is happening with Africa and Saudi Arabia, pushing up into Europe, creating the Alps. Another example of this is the Appalachians, which were generated by orogenies that lasted a few 100 million years, and it is just one of the stages in the Pangea assemblement. This resulted from 3 distinct stages of mountain building, where you had microcontinents slamming into the North American plate, and then larger continents like Africa slamming in and leaving a part of itself behind, creating the Appalachian mountain range. And that's it for our lecture today. I hope you all enjoyed learning a little bit about earthquakes and things that it causes and how they form. And again, if you have any questions, feel free to email me, post them in our comments section, and I will see you guys